Alright, so we're continuing on with section 3.4. The charts on the previous page helped us to see when a data value is considered unusual and when it's considered to be an expected value or in the expected range. And I just want to show you an example to kind of show you how that works. So let's take a look at that now. Suppose that for a certain person the average number of Visa purchases per day is 3.59 with a standard deviation of 2.81. Would it be considered unusual if the person did not make any Visa purchases one day? And explain. So when somebody asks me would something be unusual, I usually think, well, I want to know how many standard deviations away from the mean it is, and then I can use those charts on the previous page to help me answer that. And the best way to know how many standard deviations away from the mean something is to do a z-score. So I'm going to start off by calculating the z-score here. And with the z-score, you always want to start with the data value in question, subtract the mean, and divide by the standard deviation. So they say, would it be considered unusual if the person did not make any Visa purchases? And another way you could translate that is that there were 0 purchases. And we do want to be thinking about a number, so even though the way it's worded is fine, we want to think, okay, what does that mean? It means 0 purchases were made. So that's the value in question that I'm wondering, is that unusual? And then I would want to subtract the mean, and it says here that the average or the mean is 3.59 and the standard deviation is 2.81. So subtract the mean, divide by the standard deviation, and see how that turns out. I usually do that in a single calculation on the calculator, so I'll do that over here. Sorry, I'll straighten that up for you. So clearing out our old work, and then when you're doing a z-score, the way I wrote this is fine, but when you calculate it, you need parentheses around the numerator or denominator if there's more than one number. Our denominator only has 1, but the numerator has 2. So for me, my z-score, I want it to be open parentheses 0 minus 3.59 close parentheses and divided by 2.81. Excuse me. And we also talked about the z-score always being rounded to exactly 3 decimal places. So negative 1.27, and it's a 7 but followed by a 5. So I'll make that negative 1.278. So z-score is negative 1.278 for that. And so then we're faced with that question again, is that considered unusual? And what we saw from those charts on the previous page is if you are more than 2 standard deviations away from the mean, that would be considered unusual. This is 1.278 standard deviations away, so it's less than 2 standard deviations, so this is not unusual. So let's get to that explain part and answering the question. Would it be considered unusual? I would say no. And then my explanation would be based on this z-score. I would say no because 0 purchases, which is what they asked about, is less than, and then the key number for that is always 2, so it's less than 2 standard deviations away from the mean. So if we had flipped a couple digits, if this z-score was negative 2.178, that would be more than 2 away, and I'd be saying yes. But right now, I have a z-score that indicates this is less than 2 standard deviations away from the mean, and so it is not unusual. Notice I don't say that this z-score is not unusual. They asked, is 0 purchases unusual, and so that's what I talk about. No, because 0 purchases is less than 2 standard deviations away. It's a common mistake for students to say no because the z-score is less than 2. Nobody's asking us, is the z-score unusual? They're saying, is it unusual if the person doesn't make any purchases? So make sure we're referencing that. The z-score is used because it tells us whether we're more or less than 2 away from the mean. In this case, 1.278 below. Let's look at that again. Would it be considered unusual if the person made 12 purchases in one day? I'm going to go after that in the same style. More clear what number they want here. It's about 12 purchases. I'd still subtract the mean, which is 3.59. I'd still divide by the standard deviation of 2.81. I'll still use my calculator and round to 3 decimal places. So let's see how that one comes out. Open parentheses, 12 minus 3.59, and divide it by the standard deviation of 2.81. And there we get 2.99. It's a 2, but I'll round that up because of the 8. So 2.993. So all on its own, what that is telling me right there is that 12 purchases is 2.993 standard deviations above the mean. And in the context of this question, the most important aspect of that to me is if it's 2.993 standard deviations above, then it's more than 2. And if you're more than 2 standard deviations away from the mean, in statistics we consider that to be unusual. So my answer to the question of is it going to be unusual is I'm going to say yes, and then my explanation is going to be because 12 purchases is more than 2 standard deviations away from the mean. Whether something is unusual or not has nothing to do with whether the z-score comes out positive or negative. It's about the overall distance. Is it bigger or smaller than 2? The positive, if this one would be an unusually large number of purchases. If this had been unusual because it was negative, we would have said unusually low. This is a low number of purchases, but it's not unusually low. And by the way, just worth a mention, like, who cares, right? Well, if your number of purchases was unusually high, your credit card company would care. If this activity is unusual for you, that means it would be rare for you to make so many purchases. Then if they see 12 purchases happen on your card, they're going to be concerned that that card's been stolen. They're probably going to put a hold on that card until you contact them and verify if those purchases were you, or if they were in fact made by someone else and the card needs to be canceled. So they're definitely looking at things like this, and they're probably doing it in a way that's somewhat similar to this. And they can't just use a certain number for everybody, because there are certainly some people who use their card a lot, and 12 purchases is not a big deal for them, and for some people it might be unusual. So we would use each person's mean and standard deviation when trying to decide if the activity was unusual. All right, another variation on that question is what would be the expected range for the number of Visa purchases per day? And that is how many purchases could be made and it would not be considered unusual. That's definitely related to the questions up above, but instead of saying, is this value unusual, is that value unusual, we're just saying, what are all the values that you would not consider unusual? And then anything outside of that range, therefore, would be considered unusual. So we know the cutoff is 2, so what we'd want to do is something like mu plus or minus 2 sigma, to calculate the numbers that are 2 standard deviations away from the mean. And I'll do both of those. If I do mu minus 2 sigma, that would be the mean of 3.59 minus 2 times the standard deviation of 2.81. And let's calculate that and see what we get. So 3.59 minus 2 times 2.81, I get negative 2.03. That is a number that is exactly 2 standard deviations below the mean. So if the number of purchases got beyond that, it would become unusual. Anything within is expected. And then that was the minus case. And I'll do the plus case as well. So mu plus 2 sigma would be 3.59 plus 2 times 2.81. And that is such a similar calculation to the last one. I would start off by hitting the second key and the enter key. And when I do that, that pulls up my last calculation, and I can use the arrow keys just to change that minus to a plus. Of course, you can type the whole thing in if you want, but it's not necessary if you use that second entry key as a trick. You can just do some modification. So there's our 2 numbers that are 2 standard deviations away. And there's some temptation to just say, okay, the expected range is anything between these. But when you're dealing with a variable that is discrete and the number of purchases made per day is discrete, then I think what you should think about is what's the smallest value in this range that makes sense, and what's the biggest value in this range that makes sense. And I don't think anything in the negative range makes sense. So we kind of have, let me draw a number line for you. And we have maybe 0 as the least number of purchases that makes sense. And then maybe you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and we could go on 10, 11, and so on. But we're saying with this 9.21, if you get past here, anything out there is going to be unusual. And on the other side, if you had your 0 here and you want -1, -2, -3, you have that -2.03, so anything that got past this on this side would also be unusual. But anything in the middle, that's the sort of stuff that we expect to get. And again, if it was continuous, I'd just say anything between -2.03 and 9.21. But when it's discrete, I think about what's really possible. 0's possible, 1's possible, 2's possible, 3, 4, 5, 6, 7, 8, 9. So is 10. I'll even bubble that, but that's not in the expected range. And this, you could do a dot, but that's -1 purchases. That doesn't make sense. So I'd say none of this really makes sense. So the lowest end I could expect would be 0. The highest end would be 9. And I'm going to say the expected number of purchases is anywhere between, or actually from, 0 to 9 purchases per day. So anywhere from 0 to 9 purchases per day. And one thing I'd like you to just kind of pause and think about for a second is this upper limit right here of 9.21. What if that had been 9.71? So just think about this for a minute. How would your answer have changed if this was a 9.71? What would you have done differently? So a common answer that people give when I ask that question is they say, oh, then I would say from 0 to 10. But that's not actually right. Suppose we move this fence over to 9.71. Is 10 inside? No, it's still on the outside. So it's not about rounding this number to the nearest integer. It's about imagine it as drawn in as a fence that separates what's expected and what's unusual. And we throw the ED on here. But moving that fence over a little doesn't move this to the inside. So it would still be the case. Even if that was 971, I'd still say anything from 0 to 9, because with the fence at that pink line, 9's still in, 10's still out. So this is not rounding that I'm doing. I'm really thinking what's the smallest possibility that makes sense for this variable in between these, and that's here. And then what's the biggest number in between these two that makes sense, and that's my 9. And again, it wouldn't change if that was 9.71. If this had been continuous data instead of discrete, then I would have used the word between, and I would not have adjusted the numbers at all. I don't want to use the word round because it didn't round, but I did adjust them to something that made sense. But if it's continuous, everything makes sense. So I would just say between and leave the numbers alone. But for discrete data, consider the smallest and largest possibilities that fall within the boundaries. So again, just thinking of these as boundaries and what's the smallest number inside, what's the largest number inside. Okay. All right, let's look at one final page here from section 3.4, which is the coefficient of variation. You're going to see as the class progresses on that it's very common for us to be estimating the mean and being focused on the mean, and we use the standard deviation to help us do that, but the standard deviation all by itself can also be important. Imagine you were trying to fill soda cans with 12 ounces, and you tested it and you found out the average was right at 12. Then should you be satisfied? Our initial thought might be, oh sure, if we're hitting the average, we're good. But I would say that's not true all by itself. What if the standard deviation that went with that mean of 12 was 2 ounces? Then that would mean it wouldn't be unusual for us to miss our target by 3 ounces. So what if you bought a 12-ounce can of soda and it only had 9 ounces in it? You wouldn't care that there was other ones balancing that out. You'd be mad about your can. So people in a process like that, they like the standard deviation to be small because that shows that they have a consistent product. But what does small mean? Is missing by 3 ounces bad? It can be. I would say missing by 3 ounces on a 12-ounce can of soda is horrible. But if you missed by 3 ounces when you were filling a 100,000-gallon pool, then I would say that was fantastic. So when you consider, do you have too much variation or is the variation at an acceptable level, you want to think about the standard deviation and how that compares to the size of your target, which was the mean. So the coefficient of variation helps us to do that. We look at the ratio of the standard deviation to the mean of the data set when we're doing the coefficient of variation. And what that looks like in symbols varies depending on whether your data came from population or census data or sample data. If you had population data, then your coefficient of variation, or CV, is sigma over mu times 100%, but in words that's the standard deviation divided by the mean times 100%. For samples, in words it's the same thing, standard deviation divided by the mean times 100%. It's just if it's samples, that would be a sample standard deviation S and a sample mean X bar, as opposed to population ones mu and sigma. So let's see how that plays out with an example. A supermarket has 10 registers open. Each register has its own line, and customers ready to check out pick the line for the register they wish to wait for. An electronics store has 10 registers open as well. However, they have one single line that all the customers wait in. And when a register opens up, the first customer in the single line goes to the register. The wait times at the supermarket have a mean of 5.7 minutes with a standard deviation of 3.207 minutes, and the wait times at the electronics store have a mean of 8.75 minutes with a standard deviation of 1.574 minutes. So let's calculate the coefficient of variation for each of those. We'll start out in part A looking at that for the supermarket wait times. So we want to come up with the CV, and we want to take the standard deviation divided by the mean times 100%. So let's see, for the supermarket, the wait times for the supermarket have a mean of 5.7 and a standard deviation of 3.207. So according to the formulas, we take the standard deviation, 3.207, we divide that by the mean of 5.7, and then we multiply that times 100%. That times 100% as part of the formula is optional. You could just do that division and you'd get the decimal form, and you could just convert it to a percentage by moving the decimal over, but it is usually written as part of the formula, so I'll show it to you that way. So 3.207 divided by 5.7, that would be our decimal version, and then times 100 to get that to be a percentage. And we would say it looks like the coefficient of variation is 56.26%. So approximately 56.26%. On all percentage type interpretations, it's common for us to say at least 4 decimals. Well, this has moved the decimal over, so I still have 1, 2, 3, 4 if I was thinking about the decimal version. And then let's just practice that again. Let's look at what it would be if we were doing that for the electronics store. So I'm going to just do that in pink just so we can kind of separate the numbers here. But for the electronics store, our mean was 8.75 and the standard deviation was 1.574. And so we're going to do the CV in the same way. Now that I got that kind of pink label, I'll go back to the blue. But what's our standard deviation for the pink one, or for the electronics store? 1.574. And divide that by the mean, which is 8.75. Again, that in my mind gives us the percentage just in decimal form, and I would slide the decimal over kind of on my own, but this formula builds that in by doing the times 100%, so we'll go ahead and follow that. So 1.574 divided by 8.75 and then times 100%, and as a percentage that would be 17.99%, an 8 but followed by that other 8. So 17.99%. So it seems like actually calculating the coefficient of variation is not that tough. It's just a division and then a multiplication with that 100%. So it's pretty quick to do that. Let's look at the follow-up questions and see what that does for us. Would it be unusual for a customer to be in line for over 12 minutes at the supermarket? So let's see, that's actually going back to our previous section. They're asking us, would it be unusual? So I want to do a z-score for that. So over 12 minutes, I'll look at the borderline number of 12, and this is the supermarket, so we're going to use these numbers, subtracting the mean of 5.7 and dividing by the standard deviation of 3.207, and doing our z-score. So parentheses 12 minus 5.7 over 3.207, and we get 1.964 as our z-score. So would it be unusual for a customer to be in line over 12 minutes at the supermarket? Almost. Not quite, because it's under 2 standard deviations, but it's very close. So I would say no, because 12 minutes is less than 2 standard deviations above the mean. This isn't a huge deal, but I did actually say that it's talk about above the mean instead of away from the mean. They're only talking about long wait times here, so I want to point out, no, that's not an unusually long wait time because it's not that many standard deviations above the mean. You could still say away, but I kind of like to emphasize the direction since they're talking about a specific direction. So even though the average wait time at the supermarket is 5.7 minutes, this is telling us we shouldn't be surprised if we end up in that line for 12 minutes. So we know that the average at the electronics store is higher, and we're going to look at the same question. Would it be unusual for a customer to be in line for over 12 minutes at the electronics store? And we would do that same approach. We do 12 minus, but then the mean for the electronics store is 8.75 minutes. And the standard deviation is 1.574 minutes. We go through to our z-score. Same calculation, just different numbers plugged in. So 12 minus 8.75 over 1.574. And look at that, we end up over 2. So 2.065. So there's not a huge difference between these in terms of the size of the numbers, 1.964 versus 2.065. But we had to draw a line somewhere, and we drew it at 2. And this one is less than 2, this one is more than 2. So when they ask this question, would I be surprised, would it be unusual for me to be in line over 12 minutes at the electronics store? I'm going to say yes, because 12 minutes there is more than 2 standard deviations above the mean. So I think that we have an interesting thing there. The wait time at the supermarket on average is less. It's about 5.75 minutes and 8.75 at the electronics store. And so we kind of expect to wait in line longer at the electronics store. But let's say that we were in a hurry and we needed to be out in 12 minutes. It would be a surprise if we didn't get out of the electronics store in 12 minutes, but it wouldn't be a surprise at the supermarket. And that turns out to be the case. You get a more consistent wait time with less standard deviation typically when you use one line that feeds many registers, which is the Best Buy model or the Fry's model, as opposed to the Safeway model where every checker has its own line. And that turns out to be true even if they have the same average. So as a customer, you really should prefer that you have one line feeding multiple registers instead of having to pick your line. And personally, I feel like I always pick badly and end up in the slow line. So I prefer those long lines. I don't have to make that choice. All right, let's go ahead and look at one final question here. And I think we probably kind of discussed it right up there. But if having individual lines at each register and having one single line for all registers is known to produce the same average wait time, which it is supposed to do theoretically, then is there any advantage to having a single line? And I would say yes, because the standard deviation is smaller. You have this smaller coefficient of variation, meaning you get a more consistent wait time. And people like consistency. So if the average is going to be the same, it would be good to have a consistent wait time so you don't have some customers getting through quickly but others getting frustrated in a slow line. So I would say yes, there is a smaller standard deviation deviation means the wait time is more consistent for all customers. And I would like that as a customer. There's kind of less of a luck factor in terms of how long I'm in line. And there's less frustration. I don't know. It could just be me, but I always get frustrated when I feel like, oh, I picked the wrong line, and I look at that other line I was considering, and I see that the person that took the spot I would have had got out, way before I did, and that sort of thing just isn't going to happen if you have that single line. It's kind of a more fair situation, and so they're going to that at more and more retail places to have that one line idea. I think even our bookstore here at Chabot does that during the busy times, and again, it's already frustrating what we're paying at the bookstore for our materials, so let's have one less thing to worry about did we pick the right line or the bad line. All right, that wraps up section 3.4.